This section is about higher order derivatives and some different types of applications for derivatives. Since the derivative of a function is another function, it shouldn't be any surprise that you could repeat the process and find a derivative for a derivative. So for instance, let's let the function f of x be defined as 1/6 x to the fourth power plus 2x squared. And we'll find the second derivative of f. Now we can't find the second derivative of f directly. We have to go through the process of finding the first derivative to begin with. So that's where we'll begin. Here we can use the power rule and come up with f prime of x is equal to 1/6, and the derivative of x to the fourth power is 4x cubed. Then 2 times the derivative of x squared is 2x. So we get 4 times 1/6 would reduce and become 2/3 x to the third power plus 4x. There's our first derivative. And if you'll notice, it's a function. There's no reason why we couldn't take another derivative of this function. So the second derivative, we notate that with the prime notation by using 2 prime marks. So f double prime of x, you might say, or generally just the second derivative of f. Then it would be 2/3 times the derivative of x cubed, which is 3x squared, plus 4 times the derivative of the function x, which is just 1. So simplifying, the 3's will cancel. So 2/3 times 3 is just 2. So 2x squared plus 4. And that's our second derivative. And if you can find a second derivative, it isn't much of a stretch to think that you could do a third, a fourth, a fifth, or even further. So let's find the third and fourth derivatives of this function. The third derivative, it's not as common to do a third or fourth derivative, but there's no reason you couldn't do that. The third derivative, we use 3 prime marks. Okay, and when we find the third derivative, it would be 2 times the derivative of x squared. So bring the 2 down, multiply it against that 2, so 4x. The derivative of the constant 4 is 0. So 4x is our third derivative. Our fourth derivative, there's different ways of notating it. I've seen like Roman numerals for prime marks, and I've seen putting an integer in parentheses, as long as you understand what's being told. Again, a fourth derivative isn't all that common, so it's not like you'd use this notation very often. But regardless, the derivative of 4x is just 4. So we could continue the process. And that's what's meant by higher order derivatives. If you'll notice, when you're doing repeated derivatives of polynomial functions, each new derivative is resulting in a simpler function, because we've gone from starting with something to the fourth power, and now we're down to a constant. However, if we were to do multiple derivatives of a function requiring the product or the quotient rules, the algebra involved can quickly become very complex. And at this point, we don't have enough knowledge of derivatives to perform these, but we will soon see these later in the course. And I want to make sure you know how derivatives are notated, the higher order derivatives, that is. So beginning with what we call prime notation, which we have the first derivative as f prime of x, for instance. We have the original function f of x. Its first derivative is f prime of x. The second derivative, as we saw, f double prime. Then f triple prime. And then sometimes you could switch and use Roman numerals. Other times it's just to put the number of the derivative that you're doing in parentheses. And the parentheses are important if you're going to use a number, because that way it's interpreted as a derivative rather than an exponent. And then continuing on, the pattern stays the same. You just keep putting different values of n into that derivative function. We also have Leibniz notation, and Leibniz is a mathematician who was a developer of calculus and came up with a notation for different operations in calculus that are very useful. Not so much shorthand constructs, but very useful the way they're written. So if you have a function y, and this would work as well if you have it written as f of x, but it's more common to see as y, then the first derivative we've seen as dy dx. Okay. The second derivative is a little bit odd. It's d squared y over dx squared. And that's how we notate the second derivative. The d in the numerator means the derivative of y is your function. So you're saying here the second derivative of the function y, and then the square in the denominator means that you're taking the derivative with respect to x twice. So the way it's notated, it's recognizable as a second derivative, and that's what's important. Third derivatives or higher, you just follow the same pattern. Now let's talk about interpretations of derivatives. We've done some interpreting, but let's formalize a couple of things that are really important. So one thing we need to do is make the assumption that on a closed interval from a to b, that b is always greater than a. Now, that's not really an assumption that we have to make. That's just how intervals are set up. Whenever you're using interval notation, smaller number comes first, the larger number comes second. It's a rule in interval notation. When we're reading graphs, we always read from left to right because we're going from the smaller numbers to the larger numbers. But I just want to point it out in case you weren't aware that that was always the case. And because of that, if we look at the formula for an average rate of change on an interval, the average rate of change of some function would be f of b, the endpoint, minus f of a, the starting point, divided by b minus a. b minus a, if we know that b is greater than a, you can rearrange this formula. You could subtract a from both sides, and you can say that b minus a is greater than 0. So if b is the larger number, b minus a is always going to be a positive value. And that's an important thing to understand because the denominator of this fraction is always positive. Okay? And because it's always positive, whether or not this average becomes positive or negative itself is solely dependent upon the numerator. So the only way this could be positive is if f of b is greater than f of a. And that would mean that f of x is on an increasing interval. So let me show you a graph. Now, when it comes to determining intervals of increase or decrease, you answer along the x-axis. So you can see the function right through here, going from left to right, is increasing in value. All right, clearly the function is increasing. And the reason I know it's increasing is because the y values are getting larger as I go from left to right. So on the x-axis, I'm increasing on the interval from negative infinity all the way up to this point right here. Now, this particular point at 0 for this graph, we say it's neither increasing nor decreasing. So I'm going to leave it as an open circle. Now, on the other side of this point, the function is entirely decreasing because the y values are getting smaller. So on the x-axis, that's this interval right over here. Okay. Now, as we go from left to right, b minus a, no matter what 2 points we choose. So suppose I choose the points, let me start with some positive numbers. So let's say I choose the point 1, and then the point 2. Okay, so there is some value associated with each one of those points. So this is x equals 1 and x equals 2. Up here, this is y equals f of 1. And right here, this is y equals f of 2. Now, to be perfectly honest, I'm not so much worried about what the value of f of 1 is or what the value of f of 2 is. Looking at the graph, f of 1 is approximately 5.7 maybe, and f of 2 is approximately 4.2. It's hard to really be very accurate there. But I'm not concerned with that. What I'm concerned with is the fact that f of 2 is less than f of 1. Okay? And because of that, I can say, just by subtracting f of 1 from both sides, f of 2 minus f of 1 is less than 0. So the difference between those in that particular order, from the largest minus the smallest, is less than 0. Which means if I try and evaluate the average on that interval, it's going to be f of 2 minus f of 1 divided by 2 minus 1, because you always go in the order from the largest minus the smallest. The numerator is less than 0. The denominator is always greater than 0. So what happens is this is a negative number. What that means is this is going to be a negative number on any interval that is decreasing. Likewise, if I try values over here on the increasing side. So let's say I use -2 and -3. So -2 has some associated y value. It would be y equals f of -2. -3 has an associated y value through this function. So y equals f of -3. Now, if I am trying to determine how the positive and negative values of these y's relate, f of -2 is greater than f of -3. And remember, in order of negative numbers, -2 is larger in value than -3. That's why I started with the positive numbers, even though it was a decreasing side. In that case, we can say that f of -2 minus f of -3 is greater than 0. And what that means is on this increasing interval, the average value is going to be f of -2 minus f of -3 divided by the difference between my x values, which would be -2 minus negative 3. Negative 2 minus negative 3, if you'll notice, is negative 2 plus 3, which is positive. Of course, it's positive 1, but my point is this will always end up being positive in the denominator because we're going from smaller numbers to larger numbers. F of negative 2 minus f of negative 3 on this increasing interval, we've already determined that that's going to be a positive. And a positive divided by a positive results in a positive value. And that's going to be the case on any interval that is increasing. So what we can determine here is that since the derivative is just a limit of the average rate of change, and that's what we just calculated here, it would follow that if the derivative is positive, then that means the function on that interval is increasing. And likewise, if the first derivative is less than 0, then we have average values that are less than 0, which means we're on an interval that is decreasing. So that would tell me that f of x is decreasing. And finally, if the first derivative is 0, that tells me that the function is constant. And that's actually a rule that we knew already, because the derivative of a constant is equal to 0. So the reverse is true. If you have a derivative that's 0, that came from an interval of a function that was constant. One common application of derivatives and higher order derivatives is the relationship between position, velocity, and acceleration. If a function s of t represents the position of an object at any time t, then the average rate of change of that object over some interval of time is defined as the average velocity v of t equals s of t2 minus s of t1 divided by t2 minus t1. So this average velocity is the slope formula. And so an average velocity is the slope between two different positions of the object through time. If we were to allow t2 to get closer and closer to t1, so get those 2 points of time to be very close to one another, we could take a limit and arrive at the instantaneous velocity at a single point, which is the derivative of position. So velocity is the first derivative of position. Similarly, the average rate of change in velocity over a specified time period is known as the average acceleration of the object, because how quickly an object is changing speed, that's what's known as acceleration. And you can get acceleration as an average using the slope of the velocity with two different points in time. But just as we did with velocity, if you allow t2 to get closer and closer to t1, so you allow these two values to approach each other and take a limit, then you're getting the average velocity at a point, which gives you the instantaneous acceleration. So the acceleration function is the first derivative of velocity. So their general relationship here is velocity is the first derivative of position, acceleration is the first derivative of velocity, and the second derivative of position. Now velocity is a directional quantity, meaning that it can be positive or negative, but sometimes the direction is not really all that important, and so we also define what's called the speed of an object, which is not directional. And so the speed is the absolute value of velocity, and taking the absolute value removes If it's a negative velocity, that is, it removes the negative. If it's a positive velocity, it stays the same. So it just gives us how fast the object's moving without respect to any sort of directional component. Let's do an example. If an object moves according to the function s of t equals 0.5 x cubed minus 6 square root of x plus 4, find a, the average velocity of the object on the interval from 4 to 9, b, the instantaneous velocity at t equals 4 seconds, and c, the acceleration of the object at t equals 2.5 seconds. Okay, so starting with A, we want the average velocity. Which I'll notate with v with a bar over it. So that's average velocity, that's fine. In order to get the average velocity on the interval from 4 to 9, what I need to do is take my position function evaluated at the larger point minus the position function evaluated at the smaller point divided by the difference between those two. Notice 9 minus 4 is, of course, a positive number. So whether or not this is positive or negative is solely dependent upon the numerator. Now, s of 9 and s of 4, I think I'll come off a little bit below here and calculate those separately. So s of 9, according to my function, would be 0.5 times 9 cubed minus 6 times the square root of 9 plus 4, which I think I should use a calculator for. So 9 cubed should be something large, so 729 times 0.5. Then I need to subtract 6 times the square root of 9. The square root of 9 is 3. Then plus 4. So 350.5. So seems large, but we don't know what the actual units are here, so who knows? Maybe it's only going inches per second. Who knows? Anyhow, s of 4, we would take 0.5 times 4 cubed minus 6 times the square root of 4 plus 4 and see what we come up with here. So 4 cubed is 64 times 0.5 is 32 minus 6 times the square root of 4, which would be 2, then plus 4. So that's 24. Okay, now the average velocity is the value that we came up for s of 9, which is 350.5, minus s of 4, which was 24, and divided by 9 minus 4, which is 5. And again, that's something that will be useful to do in the calculator. So 350.5 minus 24 divided by 5. So 65.3. And this wasn't given to us as feet per second or meters per second or anything. So whatever the units are is something units per second. Part B, let's find the instantaneous velocity at t equals 4. So the instantaneous velocity restart it again. We find this by doing a derivative. So the velocity function, sorry, not the average, the velocity function is going to be the first derivative of the position function. that's what we need to come up with. So the position function we had as 0.5x cubed minus 6 square root of x. And instead of square root, I'm going to make it to the 1/2 power because that's easier to use in the power rule. Then plus 4. All right, so velocity being the first derivative of position would be 1.5 x squared minus 3x to the negative 1/2 power. Whoops. Try writing that a little bit better. 1/2 power. And the derivative of 4 is 0. So this becomes 1.5 x squared minus 3 divided by the square root of x. So the instantaneous velocity at t equals 4 would be the velocity function evaluated at 4, which is 1.5 times 4 squared minus 3 divided by the square root of 4. And I'll use the calculator to come up with that. So 1.5 times 4 squared, which is 16, minus 3 divided by the square root of 4, but since the square root of 4 is 2, I'll just write minus 3/2. So 22.5 is the instantaneous velocity at that particular point in time. Lastly, in part C, what we want is the acceleration of the object at t equals 2.5 seconds. So the acceleration is the first derivative of velocity. So if I take my velocity function that I just came up with and want to develop the acceleration function, that is the first derivative of velocity. And since velocity is 1.5 x squared minus 3x to the negative 1/2, I'm switching back to the negative 1/2 power because that is easier to use the power rule with. And then acceleration is that first derivative. So that would be 3x plus, so bringing the negative 1/2 down times the negative 3, that gives me positive 3/2, x to the negative 1/2 minus 1, which would also be negative 3/2. So it looks like I have 3x plus, sorry about that, 3/2, so then it's x to the 3/2 power. So what I'll do is write it as 3 divided by 2x to the positive 3/2 power. Okay, now evaluating this at t equals 2.5 seconds will give me the acceleration at that particular point in time. So 3 times 2.5 plus 3 divided by 2 times 2.5 to the 3/2 power. And that's a nice operation for the calculator to do. So 3 times 2.5 plus 3 divided by, and since there's a product there, I'm going to put quantity here. 3 divided by 2 times 2.5 raised to the 3/2 power. A lot of parentheses there. You can do it in multiple steps to make sure you get the correct answer. But 7.9. That's our acceleration. Now again, we never specified what units of measure we had here, if it was feet, inches, or whatnot. but we did specify time, which was seconds. So whatever our units are, the position is measured in those units. The velocity is that unit divided by seconds, so units per second. And then acceleration is units per second change per second. So it's actually unit per second squared. So if you have like meters per second squared, that's telling you an acceleration or a measurement of acceleration. Anything which is a distance over time squared. All right, another example, cost and revenue. In these examples, we let c of x be a function defining the cost of producing x units of a good, and r of x be the revenue in selling x units. So revenue is pretty simple the way we calculate things. It's just the price of the item multiplied by the number of items sold. So if p of x represents the price, and the price can vary, then the revenue is r of x equals x, the number of items sold, times the price. This allows us to define the amount of profit realized in selling x units. So the profit is the revenue of selling x units minus the cost of producing x units. What we're mainly interested in how these functions apply to calculus. So the concept that you really need to know is that the term marginal added to any of these indicates a derivative and is interpreted as cost, revenue, or profit of producing one additional unit of good. So for example, if the cost of producing x units of a good is given by c of x equals 0.005 x cubed minus 1.25 x squared plus 1800, find the marginal cost of producing the 53rd unit. There's nothing to manipulate with these formulas here. This isn't a business calculus course, but asking you to find a marginal cost is a reasonable question. Marginal cost, that's just another way of saying find the derivative of your cost function. Okay, so power rule. So 3 times 0.005 would be 0.015, and then it's x to the second power since we reduced that power by 1. 1.25 times 2, this would become minus 2.5x. Then the derivative of 1800 is 0. So the marginal cost of producing the 53rd unit would be 0.015 times 53 squared minus 2.5 times 53. And we'll use the calculator here. 0.015 times 53 squared minus 2.5 times 53. So negative 90.37. Right? So what that means is the cost is decreasing to produce each unit. And so at that particular point in time, it would be probably a good idea, depending on how profit is changing, but probably a good idea to produce additional units because the more you produce, it's costing you less to do it.